Okay, there is no one in the waiting room anymore, so I suggest that we start this webinar today. So, hello everybody, and welcome from my side to this second webinar of the Summer Space Academy, a series of webinars designed to introduce you all to exciting topics in space. The Academy, for those of you who don't know, is also part of the Astronaut for a Day contest, which is taking place in 3 countries this year as a joint collaboration. Those 3 countries are Luxembourg, Estonia, and Austria. And my name is Julia. I am from the Austrian Research Promotion Agency, or in short, FFG. And well, today, as you might have guessed already, it's Austria's turn to host this webinar. So we're delighted to have you join us today as we continue our journey through space together. A quick side note, the webinar will be recorded right now, so you can also rewatch it at a later time on the Luxembourg Space Agency's YouTube channel. So our speaker of the day is Mr. Gerhard Paar, who you can also see already, a distinguished researcher and head of the Space Robotics and Instrument Team at JOANNEUM Research in Graz in Austria. Well, besides coordinating quite a lot of EU projects with international partners, he is also co-investigator of several instruments on, for example, the ESA ExoMars Rover mission, but also on the NASA's Mars 2020 rover mission with the Mastcam-Z camera on it. Additionally, he is a member of the science team for NASA's MSL Mars rover mission and ESA's Hera mission to the Didymos asteroid system. Well, I could go on and on about his incredible engagements and accomplishments so far, but I don't want to take up all the time, as I'm sure we're all excited to learn more about Mars exploration in 3D. Very much looking forward to that. So with that, let's warmly welcome Gerhard Paar, who will now take us to Mars. Gerhard, the floor is yours.
Good morning. Thanks, Julia, for the nice introduction. Yeah, it's true. This is about Mars. I'm presently staying in Graz in my office, which is located in Austria, second largest city in Austria. I'm with JOANNEUM Research, which is the second largest non-university research organization in Austria. We're doing quite a lot of things, and one of them is actually industrial computer vision. And that's where I come from. So I come from items like tunnel reconstruction, like geology in tunnels, supported by 3D vision, by cameras, laser scanners, all these kind of things. And this technology can also be used in space and vice versa, because we have to deal with natural surfaces. We're dealing with unknown terrain. We're dealing with navigation. We're dealing with mapping and visualization. So it's pretty much the same business that we're doing on Earth and on Mars, technology-wise. Julia already did this introduction, so you still have this list of involvements of mine. I'm personally also interested in space, so this raised my attention already as a kid, I would say. So with the age of 12, I received a telescope, and even as a student, I carried it up to the mountains at times to watch the stars. And now we are on the stars. We are on Mars, and this is about my today's talk. So it's mainly about cameras. It's about cameras on Mars, what you can do with them, why we are doing camera technology on Mars, how this technology is working a little bit. I wouldn't show too many formulas or any technology details, but I think the most important one is the examples where you see how this technology and the science can be used to get information about Mars that maybe we cannot even learn from Earth, because on Earth we have a lot of plants and we have a lot of erosion by the atmosphere, which is not so much the case on Mars. So we can look back billions of years on the Martian surface to the actually the start of the solar system time-wise. So it's kind of a time capsule that we are driving on this nice red planet. Well, there's the main topic, the main target, why we do this is science. So I will show one or two science highlights to explain why and how we can use this imaging stuff also for science. And of course, I will answer your questions at the end. Now, this mainly focuses on the Mars 2020 mission, which landed quite some time now ago on Mars. 4 years ago. It consists of a rover, and you may also know the Ingenuity helicopter that got stuck in the dune, I think about a year and a half ago. But it did an amazing job being the first flying item on another planet. Perseverance is a car-sized rover. It's actually the 5th NASA rover on Mars with a very successful cadence. As you see, 900 kilograms, driven by nuclear power, which is a small element that always gives some heat, and using this heat you can get electric power. It's like a steamboat, if you wish. It's got a couple of cameras on it. The most important for us, of course, is this Mastcam-Z, which I will show in a minute. And there's also some other instruments that gain us very much information on various sources, like radiation, like different wavelengths, like wind speed, and all these kind of things. You can deem it as a geologist on Mars that is remotely driven by an Earth team. Right, and Mastcam-Z, as I said, is a zoomable 2-camera system, and 2 cameras are being used for all the 3D stuff that we're doing. So it's like the human eye. You have two eyes, because the 2 eyes, they are looking at some slightly different angles on each of the close range items that you see. And from this, the brain calculates a 3D model. And we are doing basically the same with the 2 zoomable cameras. Zoomable because then this makes us very flexible. Whether we want to see a lot of the landscape, then we take the wide angle, or we want to zoom in to have a higher resolution at a specific site. Then that's the second mode, and we have some modes between that we can select. Now, this is about the landing, which is a very thrilling stuff. You can imagine it landed on a crater called Jezero, and that worked with the parachute, of course, first. Then the rover was deployed by a so-called sky crane on the cable, so there was no lander, just the rover was dropped by the sky crane, and then the sky crane was jettisoned from the rover, and all that was captured by camera. And we were watching this in the family in our music room, and that was really exciting. And I was very glad, because all these preparations, because you can imagine there is years of preparation in order to get ready for that one moment when you get the first images. So that was really a very nice moment when also the rover ground control team told us everything is okay. Now, why do we have this to take these images? There's a lot of objectives that we want to fulfill and need to fulfill. So also your eyes, they are the main instrument, if you will, to capture context and to capture scale and size relationships, and to spot interesting spots, interesting regions around you, because you need to decide where to go. You also need to support the navigation and how you would go there, and always check where the rover is. Which route to take is also important, to take a route to the left, to take a route to the right if there's a big boulder in between, and these kind of things. And also to, of course, inform about any possible danger. And the science is not even mentioned here. Now, what about scale? Imagine this room. You would think, well, this is a rectangular room, but it isn't. It's just a kind of an illusion, if you will. And if you have just one eye, like we now have on screen, you would think, well, something's going on. This little guy is getting smaller and larger, but how does this work? Well, it's a room that is kind of bent and distorted, and I would show it I wouldn't show you. It was just to explain why we need scale. And all these objectives, they need scale, right? So we need to have, it's written anyway, where to go, you need to measure. You need to measure speed, you need to measure dimensions, you need to measure areas and heights and all these kind of things. So all this requires 3D, and that's why we are using Mastcam-Z. Now, we have a couple of missions that Julia already mentioned. One of them is the Mars 2020. There's also ExoMars, which is mostly the European mission to Mars in the next few years. I would say it's now designed to land on Mars in 2030. And here we are involved in the 3D vision on several camera instruments. The PanCam is the scientific instrument, but there's also the engineering, as we call it, instruments like the navigation camera and the localization camera. I won't go into detail on that, but just to tell you that ExoMars is not RTG driven, so we are relying on a solar panel, which is of course tricky on dust, but that's another item. MSL, Curiosity, landed on Mars almost 15 years ago, and that's really a long time to traverse on Mars. You have several winters, dust storm seasons to trespass, and it still works perfectly fine. There's almost no issue after all these years and dozens of kilometers that the rover already traveled. And there's the asteroid mission, again, driven by ESA, to the Didymos double asteroid system, which was hit by the DART impactor, I think in autumn 2022. And we are also involved here in 3D vision and providing the GIS, the Geographic Coordinate System, the Geographic Information System. Now, this is the rover, how it looked like, Perseverance rover, how it looked like in the assembling hall at JPL, Jet Propulsion Laboratory, in Pasadena, close to Los Angeles in the US. And it shows what are the components of the Mastcam-Z camera. Of course, there is the camera heads that are mounted on the so-called remote sensing mast, which is a movable mast. It can be tilted and panned so that it can look around by commanding. In such way, you can also put together pieces, individual images, and from these images make a mosaic, which is also a task of ours. And the second component is also important, mainly for science, is so-called calibration target, because it contains colors that we exactly know in the spectral response. You need to know that Mastcam-Z is also multispectral, so we have a so-called filter wheel and also RGB filters that give us a little bit more information about the mineralogy on the images that we see. And to control the camera, we need a control unit that is hosted in the belly of the rover. This is a sketch of the setup of all these hardware components. So you may expect it's something like your digital camera that you have in your pocket, or even the mobile phone camera. Yes and no, to some sense. So we do have the camera head, we have an electronic box, we have this CCD array, but we have this filter wheel assembly just in front of it. There's also so-called Bayer filter, which gives us the RGB content of the images, because originally this is just a black and white camera with a decent resolution. Not so a resolution as you have on your mobile phone. It's just 1600 times 1200. But as I say, when you assemble several of those images adjacent to each other, this is not a major issue. Then there's a very complicated zoom assembly and focus assembly in front of it, so that the images can be focused automatically. There's a light shade. There's also some projection. There's a small hole because the light shade traps some dust, and the dust can be shaken through this tiny little hole still onto the ground, so that it doesn't cover up at times the lenses. So there's a lot of engineering involved in this one. So the main infrastructure that we are dealing with presently is a processing service that we had developed about 20 years now, also supported by the FFG, who is also the host organization of Julia. And we have a visualization tool called Pro3D that is being developed by our partner Viavis in Vienna. And until recently, we also had a science partner from Austria, the Austrian Academy of Science that did some geologic assessment, impact structures. Now our main colleagues are from the UK in terms of the scientific exploitation, Imperial College London, who actually we write papers with them in order to prove that what we are doing has scientific impact. Right, this is a little bit complicated now, and this is per purpose. It's a complicated system, so that more or less catches the processing chain that we provide in order to process individual images into so-called data products. And the data products, they are nothing like, they are nothing more than the 3D models on the surface that we gain from the stereo vision. You can deem it kind of a computer game. So for computer games, you also need a 3D model of the environment, like in between houses or landscape or whatever you're playing. Here we are not emphasizing a computer game, we are emphasizing the reality on Mars, right? So we have to resemble the surface of Mars as accurate and as real as possible. So we need to know the geometry of the cameras. We need to be able to measure, and the measurement needs to be correct. So it doesn't just have to look nice; it needs to be correct, and that's still one more level of complexity. So this is a sketch of one of these data pipelines. So we have input, we have some processing, we have output, we can take intermediate outputs. That's, by the way, the sketch of the data pipeline on ExoMars for PanCam, LogCam, LabCam. And this is an example of how we present the data products in different colors, whatever, roughness, and all these different, let's say, interpretation that you can take from 3D data processing. And this is a setup, or a part of a setup that we use to validate the system. So we know the dimensions of these cubes, and then we can compare the directions and the dimensions on the cubes with what we have on the visualization, with what we have in reality by the measuring tape. And the validation, if it tells us that's correct, then we also assume that on Mars it will be correct. Again, and I promise this is the very last chart that I'm talking about in technical terms. So we have the images coming down, and this is called PDS-3, Planetary Data System. So all these data goes with a specific standard. Otherwise, we are talking languages that not everyone in the space community understands, but PDS is understood by everyone. We do some undistortion in order to correct some geometry of the camera. Then we do so-called stereo matching, reconstruct the 3D, generate a mesh, generate a map around, fuse all these maps. And what we get is so-called 2.5D spherical panorama. So it's nothing like a globe around your head that gives you the entire texture, what you see, what the camera had seen, and also the structure, actually a distance map that you can generate the structural visualization from. And there is some information that we have to have here. We need to have the imaging geometries, how the remote sensing mast was pointing. We have to know where the rover is located. And then this goes into a huge localization system, which is actually provided by the JPL, by the Jet Propulsion Laboratory, which gives us the attitude of the rover, and then we have to multiply some matrices, so to say, and gain these orientation matrices of the camera. And there's also another system that gives us a transform, geometric transform, gives us knowledge at each, let's say, millisecond or even microsecond. How was Mars moving in the solar system? How was the rover moving on Mars? Where was the sun? And from all this, we get transformations that give us the position of each point on the camera images on Mars with an accuracy of about 10 centimeters. So over, let's say, 300 million kilometers, we gain an accuracy of 10 centimeters, and of course, an even higher resolution on the surface at close range. So that's kind of a little bit of magic I would call it. This is an example how to explain what is the purpose of the stereo cameras again. You see that even if you blink between the two cameras, and that's already assembled from many camera images into a mosaic, left and right, you see so-called parallax. So if you look at this large rock in the close vicinity, and you see how it is displaced, or the displacement changes compared to a region or an object that is a little bit further behind, and that's the actual parallax. So we do this for every pixel on the image, and from this we get a so-called disparity map, and using the camera geometry, it tells us about the distances, and we can get a dense view, a dense reconstruction of the entire surface. Now, coming to the data products, I'm showing a pictorial example. This is not really of any science value, but at one time we did a 3D reconstruction of the just deployed Ingenuity helicopter. So that's not a picture, not a video. That's just many pictures rendered from the very 3D model that we gained from this. And for instance, here a pseudo-colored distance map. We could prove that when Ingenuity was lifted, did its first flights, it raised like 10 meters, and it wanted to land at the very same position, but it didn't. So we could prove we were about 2-3 meters away from the landing spot was a little bit distant to the takeoff spot. Although you wouldn't think about this. So this is a comparison between landing spot and after landing, between before takeoff and after landing. Sorry. Okay, now this localization that we gain from the rover team at JPL gives us exact correspondence between what we do in the 3D modeling from the rover images and the 3D modeling that is available from satellite imagery. So you need to know there's a couple of satellites that are flying in orbit around Mars. Some of them are also used as relay stations for the data transfer. So there's quite some redundancy. So we can send down a lot of data, which is good. And this 3D correspondence between the satellite and these satellites also carry cameras, and from that cameras using the same stereoscopy, also 3D models are done, which you could think don't have the nice resolution that we gained from the rover cameras, but you can overlay the rover camera data on top of what you have on the satellite. So for instance, you see this bright region resolved like 0.5 meter in texture and 1 meter in structure, and you see it almost perfectly corresponds to the location that we get from the Mastcam-Z 3D reconstructions. This is a view from above. You see some parts of the mosaics that we do, and you also see that the resolution degrades the further away we are from the rover, not only because the distance is higher, but because also the angle gets more shallow the further you are looking. And you can imagine there's a lot of distortion, a lot of occlusions, and we need to kind of cope with that and kind of compensate. You may also recognize there's a little bit of a rotation between the two data sets. That came from the so-called calibration of the system. This is being done in laboratory, but we have only a limited size of the room, and if we have a region larger than the lab, then of course all the small errors that you make in the lab, they extrapolate into larger areas in reality. Again, another example. So this gives a good impression on where Perseverance was heading in the first 100 or 200 days of the mission, because it was looking towards the first interesting so-called outcrop. An outcrop is well, I'm not a geologist, but I would explain it like a region where the underneath rocks touch the surface to some extent. So you have a lot of regolith, you have a lot of dust, but at some point you see also outcrops. You see the rocks, the side parts of the rocks, and you may see layers that indicate possibly some settlement on the lake, of if there was a lake. Actually, there was a lake in Jezero crater, it could be proven. And so, to some point, the scientists knew it from satellite imagery, but Perseverance and the instrument data taken by Perseverance could prove it. You also see some nasty little artifact that you could think, what's that? What's that guy? It is a scale bar. So scale bars are important to sketch the dimensions, to see immediately the dimensions. We could also place an avatar, by the way. We could place a human here, or a car, or a bus, or maybe an airplane further away. But for scientists, it's more straightforward to have, on the one hand, all the dimensions, as you see on the scale bar, but also the directions pointing to the north. So we see why is the sun is maybe somewhere over there to cast a shadow. Right. And now we meet the examples that I had indicated. So this one shows the resolution difference between the satellite DTM, which is the grid here, and the actual rover DTM, digital terrain model. And what you see here is a sample hole. There was a hole that was taken by the robotic arm instruments on Perseverance, and it actually took a sample here. And these samples, they are collected in the belly in so-called sample tubes. And I think there's almost 40 of them already been taken, and some are spare still. And these samples partly had been deposited on the surface of Mars as I would say, as a backup. And some of them, they are still remaining in the belly of Perseverance, ready to be taken to Earth at some time, hopefully in the next decade, maybe 35 or so. We are hoping that the so-called Mars sample return mission could happen, because this then gives us much more information. We have all the laboratories on Earth to see whether there is any indication of past life, maybe in one of those samples, or this geology in terms of really the molecular and ion distribution, these kind of things. And this is an abrasion spot. So here no samples were taken, but here let's say the cover of the rocks, they are released in order to look at the very inside of the rocks with mineralogy instruments, spectral, then X-ray and these kind of things. This is one science case where atmospheric science is addressed. You may see this little blue, bluely indicated, we call it flutes. So it's like little tubes on the surface, and they indicate the wind direction. These are erosion artifacts that, when analyzed and when statistically distributed, analyzed on the surface, they can lead to a distribution in specific areas. And from this, we can derive the wind direction within the last 20 million years. And if you find out, for instance, that this wind direction has changed, then you can do some deriving the history of the Martian atmosphere within this time frame, because there's also wind sensors on Perseverance, and we can also observe dust devils at some time. Right. Then there is another technology demonstration. We don't have just the two cameras on Perseverance. We also have different positions of the rover. And using these two different positions of the rover, we can actually use pretty much the same technology, but on a wide baseline. So that gains us much better resolution in terms of the distances. And here you see some really nicely reconstructed outcrops that are distant, that are further away. And still you can define the layers. You can measure layer width. You can measure all the directions of the layers, which is called the dip and the strike, which indicates how the layers are arranged underneath the surface. And this is much more high resolution, even on larger distances. So that's the same technology, but a different logistic approach on the image capturing. So I told you there is these samples that had been taken. They had been deposited on a sample depot called Three Forks. which is a pretty flat area, boring. And you see the rover traverse. It did depot these sample tubes at very specific areas in this depot region, Three Forks, and using our 3D reconstruction technology, we could exactly localize them. And maybe for a future mission, it makes sense to know about the centimeter position and the orientation of the sample tubes, because they may be buried under dust after a couple of years. So maybe this is still getting valuable in the next decade. We also wrote a paper on this, so we are providing all the positions and the orientation of the sample tubes for future missions. This is a little bit of a fun piece. At some time, there were some particles trapped in the sampling mechanisms, and JPL and the robotic arm team, they had a hard time to get rid of it. But at some point, they were able to release it. You see it here. Even Mastcam-Z even did a video when these pebbles were released by a little bit of shaking. You don't see the shaking because this is a time lapse still. And what we could do on this is to compare two different views, before and after these pebbles had been dropped, and even measure the pebbles and determine the shape of the pebbles and these kind of things. So that's change detection, that even change quantification, if you will. There's not just geology, but there's also the assessment of the regolith. And one of these important assessments is how the regolith behaves, or the soil behaves, if you disturb it, right? So from the so-called angle of repose, so the angle that remains if you disturb the surface, you can derive physical properties like adhesion, cohesion, even moisture, electrostatic charge, and all these kind of things. And we can do these, support all these using measurements. And this is a nice region disturbed by one of the wheels of Perseverance. So you see how fine this regolith is inside the dune. And yet another documentation. Sorry. So one of the samples was actually taken from regolith. And again, here, it's not just important to know about the depth, about the angle of repose, but also to see the surface, how it was before this drill was done, in order to maybe identify even one of the pebbles that were above the surface within the sample that comes to Earth. So then you can maybe associate which pebble it was, and from the observations that we have from camera, multispectral, before the drilling, we can see how did this sample change, how did this pebble change within the last 12 years when it was in the sample tube. So there's a lot of things to do on Mars 2020. We are also incorporated into the MSL mission. So this is not Jezero crater, but this is Gale crater. And this is just an example of also visualization of the 3D reconstructions that we gained from the Mastcam instrument. So that's not a zoomable, but just a fixed focal length in the so-called, just an example, Maria-Gordon notch, which was a very narrow gorge, you could call it, when MSL went over this pass. And you see there's even larger slopes and steep, very steep slopes, very close to the rover. And current studies are going on to determine whether the rover could disturb these structures that had been, on Mars, the same in the same situation for billions of years, basically. So if there's a small shaking caused by the rover, maybe you have a rockfall which destroys the rover. So there are some studies of our colleagues at Imperial that exactly do the same in this area. And we're providing some databases for this. We are working on the enhancement of our methods continuously. So this is an example on how AI could improve, or can improve actually. So the development is already finished, and we are using this also for products because you have a lot of noise the further you go, you can imagine. And to mitigate this noise by AI, that gives you still the truth. So it doesn't filter, it doesn't just smooth out, but it really gives the truth from structure that the AI had seen on Earth on 1,000 other cases, right? So that works pretty well. You see it in this example again, and from another view, you see that here, this is the regular processing. We have still some distortions, all these, let's say, well, spikes, you could call it, and those spikes are not here again, but still the shape is the same. It is more true. It really resembles better the truth. We did some validation of this. Again, another view on a pebble. I think this is about 10 centimeters. Yeah, 20 centimeters. We see it from the scale here. And distance like 30, 40 meters. And using the regular processing, you cannot do anything with this data. But now, if you have this pebble in its round shape and its true shape, you can still do some measurements, directional ones, and so on. Right. I think that's my last but one slide. We're also involved in Hera, and that's just an example how we reconstruct an asteroid. We don't have the full asteroid yet. We don't have shape at all on the Didymos, on the Dimorphos that was hit by the DART mission. We don't know about the shape change. So that was the very last image that the DART mission took before it hit the surface, before it exploded with a speed of 6 kilometers per second, which is, I think, 30 times the speed of an aircraft. And what we do is do the 3D reconstruction of the body, provide a framework that allows the scientists to measure on the surface, to place their instruments virtually, to find, let's say, to find associations between different instrument data in a spatially consistent way. All right. I think that's about it. This is the last but one. What is needed for such a mission, and also for the camera instruments, is so-called calibration. So you have a lot of work to do in the laboratory to find out the various features, the specific features of the camera, so that you understand the measurements that you make on the surface of the planet. So this is an example of all the geometric calibrations that we did for Mastcam-Z. Here, my colleague Piluca Cavallo is in ESA's lab, actually, to calibrate the CLUPI close-up image of our ExoMars. Then we did the calibration for ExoMars PanCam. This is Mastcam-Z. And here is what you see if you don't correctly calibrate, how the shape of your 3D reconstruction changes and gets inconsistent. So we also always have to keep an eye on the calibration also on the surface of the planet. There's a lot of publications, which is the actual reason why we do this, to publish, to find out scientific findings together with our colleagues, mostly from the UK and from the US. And that's about it. Going back to you, Julia, maybe we have a couple of questions.
Yes. Thank you. Thank you, Gerhard, for this nice presentation. It's really, there were quite astounding insights that you showed us. I think I'm still missing words for myself. There goes a lot of work into those different stages as well. So yeah, as Gerhard said, we are opening the floor for questions. So you can either type it into the chat, or you can also raise your hand and just speak out like I just did now. Okay, so I have one question, or one hand raised here from Tatiana. Would you like to start with your question?
Yes, thank you. Good morning, everyone. From which orbit altitude are Mars satellite images taken?
Can you read the question? It was pretty.
Yeah, sure. From which orbit altitude are Mars satellite images taken?
How many? How many images? Is your question?
From I will repeat. From which orbit altitude are Mars satellite images taken?
Okay, the orbit altitude. Well, I'm not so much concerned with satellite imagery, but I would assume there is distances between 200 and I don't think less, for 200 to 400 kilometers. But I would have to make an internet research the same way as you.
Does that answer the question?
Yes, thank you.
Okay, thank you, Tatiana. And we have one question in the chat. How far can the rover create a DEM of the terrain?
That's a perfect question. Yeah, that really depends on the zoom value that we select from Mastcam-Z. Of course, we can generate the DTM up to, let's say, 2 kilometers, but then the accuracy of the range measurement drops or goes up to 2 kilometers as well. So we can decide whether a point is 1.5 kilometers away, and we recognize that a point at 2 kilometers is further away, but we cannot measure. Real geologic measurement in the best zoom setting, which is the 110 millimeter focal length, is possible up to a distance of 40, maximum 50 meters. So the useful DEM that you can generate stops at the distance of 50 meters. We can a little bit extend this by the AI that I had shown. If it's real steep walls that you look in a perpendicular way, then you could extend this to 100 meters, I would say. But I was mentioning this, as we call it, white baseline stereo, that uses two different positions of the rover for these parallax calculations. And here you can even raise this to 200 or 300 meters until the resolution of the images gets lost. So, and you cannot measure in a geologic sense anymore. So there's different use cases that you can cover. There's different imaging logistics that you have. So this is not a fixed value, so to say.
Thank you. Do we have more questions, either in the chat or speaking up? Yes. Okay. Dario, you have one question or one follow-up question?
Yeah, thank you very much. Can you hear me?
Yes.
Yes.
Okay, perfect. So yeah, it's based on the last question, by the way, because I'm working with high-rise DEM, which is more or less 1 meter per pixel resolution. So I was wondering, what's the maximal resolution that you can reach with the DEM that you can create from the rover? Do you know, or do you have any like?
Yeah, that's distance-based again. So you may know that, or you know for sure that the stereo range distance drops by the square of the distance. So at very close range, if we are just looking kind of in front of the rover, I think we can gain a DTM resolution of better than 1 millimeter, so 0.5 millimeter or so. Of course, the image resolution is better then. But using the AI technique, which also uses just the image, you can do it even better. So maybe get down to 0.25 millimeter, and this drops by the distance. So and I think the sweet spot between the high-rise 3D resolution, which by the way can also be enhanced by AI techniques, is kind of like in 50 meters or even 100 meters, where we have to switch over to the high-rise because the rover image products they resolve worse at that distance.
Great, thank you very much.
We have one more hand raised from Gabriel.
Hello, do you hear me?
Yes.
Yes.
Thank you for your presentation. It was really nice to look into the science of the camera technology. Do you use any kind of laser measurements for the robot to show the distance and how it corresponds with the camera?
No, there is no distance, no active distance measurement, because it was shown in past missions that the stereo vision works perfectly fine on these natural surfaces. This is not always the case on Earth, as we know. So, as we know, cars, they are using lasers because they are more robust. They give more stable range measurements. But no, there's no reference measurements from active laser ranging systems. There is a laser on the surface, on Perseverance, which is a supercam instrument, but the laser doesn't measure ranges. The laser uses a very high power laser to generate little explosions on the surface to measure ions. But this is a completely different instrument and doesn't provide range. I don't know about any rover, any lander instrument that really has a laser scanner on board. There's only satellites that do have. You may know the MOLA system that actually mapped entire Mars from orbit. But I think there's no rover system that's doing any range using lasers.
Do you know why? Because you mentioned before the lasers are more robust. So
yes, they are more robust on surfaces that don't provide that nice texture that we have on the natural surfaces of Mars. So stereo is still robust on these natural surfaces. So we don't have the case that stereo may fail at some critical point. And you know, we need power for lasers. We need also a pointing device, yet another pointing device, in order to place this laser spot around in a grid. So that also takes power. That is risky. That's yet another instrument. And cameras you have anyway, right? So there was no need, and nobody argues.
okay, thank you.
Thank you, Gabriel. We have one more question in the chat from Alberto. How long does it take to process the Mastcam-Z images into 3D images? Does it depend from the specific goal you have, or are there different types of calibration that must be done?
Okay, so for the 3D, that's actually the most time-consuming process, I agree. It's about half a minute of an image pair. So if we get a mosaic of 100 images, then that's about an hour or so. So it's really the time it takes is really more the time it takes to bring the images down to Earth via the Deep Space Network. So the rover actually first records the images. Then when the plan has been finalized, it prepares this data bundle to send over to one of the relay satellites when they pass over the rover. That takes time. Then these satellites, they need to be in a position that they can relay this information. So they store it, they can relay this information back to Earth. And on Earth, it's again distributed, processed to get all the metadata. So that's a real, quite some logistics to bring the images down. And it's the smallest deal then to process them time-wise. So that's, I think, yeah, as I said, in 1 hour, you can process an entire panorama in 3D.
Okay, I think that answered the question. Do we have one more? Maybe we can take one final question, if there is any.
I have a little question while everyone else is thinking. Maybe somebody else comes up with something as well. Since you mentioned focal lengths, actually, and I do quite a bit of photography here on Earth, so I was wondering, how do you pick the right focal length when you go on a different planet? You mentioned, I think, 110 millimeters. You said that's ideal. So I was wondering what makes it ideal and what other focal lengths are in use.
Yeah.
And also, I remember I read this article recently about how they do this kind of 3D thing on smartphones, where you know how smartphones nowadays have several cameras, and they take pictures simultaneously with the different focal lengths, and they create a 3D model based on that. So I was wondering, is that also how it's done in space, or when you have two cameras on the rover, are they the same focal length? So how does that work?
Yeah, it's not just a different focal length. I think these cameras they also have maybe a stereo system, or they have a projection system which works at close range mostly. So that's really completely different technology. So I would say no, we cannot do anything with different focal lengths in the 3D domain. So we cannot derive just from one camera and different focal lengths a 3D model. That's not possible with these kind of sensors. On the ideal focal length, well, I mentioned it gives you the best resolution, but in a data amount sense, it's not ideal, because you have to make many more images for the same region. If you zoom in a very small region, right? So you have to put even thousands of images to get a full panorama around. Which we did at some time, but it really takes a week or so until you get this down, and that's taken longer than an hour for processing, I tell you. So there is really a trade-off planning going on Earth, and there's a whole team sitting together like half an hour or 45 minutes to decide which zoom value to for a specific region to take, because you have only limited resources in terms of time on the surface to take the images, limited resources to downlink the data. You have, on the other hand, some needs to resolve a specific bit of surface in, let's say, 2-4 millimeters, because you need to decide about spectral response on a specific spot. So there's a real trade-off going on, and there's a complicated planning tool that mixes all this information and gives you parameters that you're interested in. So we're using basically 7, as we call it, canonical focal lengths, which is 26, 34, 48, 63, 78, 100 and 110 millimeters, from which actually the 110 and the 34 are used the most. And the 110 has a little bit of an issue in calibration, so we're not completely sure how it geometrically behaves, whilst the 34 has actually perfect calibration. So there's other aspects of the trade-off going into this decision.
That's great. That's very detailed. Thanks.
Right, thank you. There was no other question incoming, so I guess we can come to the end of the webinar. So first of all, thank you, Gerhard. I think I speak for all the participants today if I say that was a really great presentation. Thank you so much.
Welcome.
I'm sure people can also reach out to you if they have more questions. Maybe if they can also reach out to myself if they want to from the FFG. And that basically brings me to the last reminder. And Jordan also posted it in the chat already. So next week, we will have our next and already final webinar, our final session, same day, same time. A space psychologist from Estonia will talk about inside the astronaut's mind, preparing for the teamwork challenges of space. Also quite an interesting topic that we were going to hear about. So make sure to register for that as well if you haven't done so already. And I'm looking very